Tonight on Nova. Columbus sailed these waters 500 years ago. Today they're home to submarines, strange organisms, and sharks. A mysterious current that changed the course of history. Now science is taking a closer look. Join author Bill McLeish as he takes us on a journey, adrift on the Gulf Stream.
Funding for NOVA is provided by Prime Computer, supplying integrated computer solutions to the world's manufacturing, commercial, technical, and scientific marketplaces. And the Johnson & Johnson family of companies, supplying healthcare products worldwide. Major funding for NOVA is provided by this station and other public television stations nationwide.
This is the North Atlantic. Nearly 14 million square miles where wind, water, and the spin of the Earth combine to create the most remarkable oceanic current in the world, the Gulf Stream. An ocean giant transporting almost 100 times more water than all the rivers in the world combined. The stream and associated currents influence weather and climate from North America across to Europe. These currents have shaped human destinies, helping some along their way to discovery and colonization, hindering others who try to sail against them. The stream provides pockets of productive water where fishermen find heavy catches. Its twists and turns provide hiding places for submarines. Marine science today uses sophisticated techniques for measuring the stream and predicting how it will behave. In this program, we will look at some of these modern techniques and at the many mysteries, physical and biological, that still remain to be solved. We'll be voyaging around the North Atlantic on the Gulf Stream and its sister currents through 500 years in history. We start here in the eastern part of the Atlantic Ocean, where the influences of the Gulf Stream are most surprising and mysterious. An enchanted place, a maritime climate, mild and full of mist. This is Dog's Bay, near Galway on the west coast of Ireland. If you're lucky, you can find curious objects on that beach, like this sea bean. It's called a sea heart. The parent plant grows thousands of miles away in the Caribbean. How did this bean get here? I'm Bill McLeish. For the past 3 years, I've been researching a book and this program about the Gulf Stream. All oceans have currents, but the Gulf Stream is the most powerful current of all. It carries more heat from the tropics to colder climes than any other current. With associated flows, it forms a great swirl in the North Atlantic that transports not only water, but nutrients and numberless animals and plants, probably including this bean. The sea bean isn't the only stranger to these shores. This is a cabbage palm, really a giant lily from New Zealand. These plants grow elsewhere, yes, but consider our location. I'm standing on a spot which is farther north than the major cities of the United States and Canada, almost as far north as Moscow, and yet subtropical vegetation flourishes here. Why? The answer is complex, but the Gulf Stream clearly has an influence. According to his own writings, Christopher Columbus visited the western coast of Ireland as a young mariner aboard a merchant ship. At the time, the conventional route to the Orient and its riches was around Africa and to the east. But some thought a ship could reach China more directly by sailing west. Columbus was obsessed with this idea. Mariner's lore and exotic objects like the Sea Heart floating ashore convinced him the western route was possible. The last of Europe Christopher Columbus saw as he sailed into the unknown was this headland in Portugal. Columbus traveled the southern arc of the Gulf Stream gyre, that swirl of currents that forms a great ellipse in the North Atlantic. We will parallel his voyage aboard the topsail schooner Welcome. It is 500 years later, but the size and speed of our ship is not much different. Welcome's rigging descends from that of Columbus's favorite ship, the Nina.
All right, go ahead, Mike.
We sailed with the trade winds that drove Columbus west. We ride the same ocean currents, whose courses have changed little over these centuries. Our rate of travel through the sea and the sights along the way are much the same.
Stand by.
Standing. Welcome's master, Arthur Snyder, checks our position with a sextant. 33, 57. What do you got?
22 degrees, 42 minutes, 4/10.
Columbus might have carried a primitive version of this instrument, but he relied on taking star sights, often just with the naked eye, to get an idea of latitude. Columbus had no means of accurately judging his speed, just guesses of how fast a floating object or a spot of sea foam drifted by his ship.
Start.
6, 7, 8, 9, 10, 11, 12, 13, 14, 15... To record our rate of travel, we use a mechanical speed indicator, which is far more accurate. 45, 46, 47, 48, 49, stop!
29 seconds.
That's not bad. 50 counts in 29 seconds means that we're moving at a little over 5 knots.
What does the log read?
About 485 nautical miles.
485 miles.
Yeah.
Puts us approximately here, which means we've come about 120 miles since yesterday at this time. And we're headed on this southwesterly course toward Antigua.
The wind roses on the chart show the force and direction of the prevailing winds. We know where we are. Columbus, of course, had only a vague idea. The northeast trades?
That's exactly right. And these green arrows here show the force and the direction of the north equatorial current that's going in a southwesterly direction. We've got about a half a knot of current with us that's pushing us right toward Antigua.
As they were for Columbus, the Canary Islands off the African coast are the last sight of land before Welcome's voyage across the open Atlantic. Crossing with the trades can be unpredictable, but this time the prevailing winds stay with us. Columbus's crew noted the constant winds and even became concerned about being able to sail back home against them. Welcome carries a full complement of charts. Christopher Columbus may have had a chart or two. If he did, it probably looked something like this. Note that there is fairly clear sailing from Spain to the Indies and the Orient. No American landmasses in the way. On a modern map, Christopher Columbus's first crossing of the North Atlantic would look something like this. From the Canaries, almost straight across the ocean, to the Bahamas. That's a distance of about 3,500 miles. The voyage took him a bit more than a month. Columbus, and for that matter, mariners for centuries after him, have no real way of tracing the course of a current in the open sea. Therefore, Columbus knew nothing of the North Equatorial Current, the Florida Current, Gulf Stream, or any of the other flows that make up that gyre in the North Atlantic. Now, Columbus did have some help from currents as he sailed. We probably had more. By sailing further south, we got a significant boost from the North Atlantic Current, the equivalent of perhaps 200 miles. It took us only 19 days to sail to the Caribbean. Even so, land was a welcome sight. We can only imagine what it must have been like for Columbus's weary crew. In his voyaging, Columbus discovered the best way to America, but he never found the best way home. Instead, he fought his way north against the trade winds until he reached favorable winds that took him to Spain. 2 decades of Spanish conquest in the Western Caribbean would pass before the discovery of a better way home. The man who made it was a fiery conquistador named Juan Ponce de Leon. Ponce was hunting for treasure and a spring of water that could cure impotence. He found neither. But while he was attempting to land on the Florida coast, one of his ships was carried northward for several hours by a strong current. That event was noted by his pilot, Antonio de Alaminos. A few years later, when Alaminos was chosen to sail to Spain with news of the conquest of Mexico, he headed for that swift water, which we know now as the Florida Current. He rode it north, hoping it would take him to the westerly winds he needed for a fast trip home. It did. That gamble literally changed the course of the Spanish Empire. Vessels by the hundreds, loaded with gems and precious metals, followed the Alaminos route. The track of the conquistadors became the avenue for colonizers of North America. The southeastern colonies in what is now the United States, even the Dutch holdings in New York, were developed with a push from the Gulf Stream system. When the colonies embarked on trade, their vessels also got an assist from the stream, which could save hours, even days, on the way to Europe. But captains of merchant vessels sailing south down the coast regarded the stream as a hazard. To avoid sailing against it, they stayed close to land. That took them near, sometimes too near, dangerous shallows like Diamond Shoals, the graveyard of the Atlantic. Even far at sea, the stream influenced maritime traffic. Yet well into the 18th century, there were no charts to mark that influence. Just before the American Revolution, that all changed. American colonists had sent a number of complaints to their agent in London about the late arrival of mail sent by packet ships from England to the colonies. The name of the London agent? Ben Franklin. Franklin consulted his cousin, a Nantucket whaleman named Timothy Folger, about the problem. Folger told him he had often seen the packets bucking the stream and slowed to a standstill by its force. Folger said he advised them they were stemming a giant current, but the British were much too lofty to listen to a simple American fisherman. Franklin asked Folger to sketch the position of the stream. The result was the Franklin-Folger map. Accurate for its time, useful even now. The Gulf Stream came to fascinate Franklin. He studied it during his many transatlantic voyages, relying chiefly on the sea thermometer. He reported, "A stranger may know when he is in the Gulf Stream by the warmth of the water, which is much greater than that of the water on each side of it." Franklin's passion for the Gulf Stream was inherited by his great-grandson, Alexander Bache. As director of the United States Coast Survey in the mid-1800s, Bache began a series of research cruises on the stream. Bache was trained in physics and chemistry and invited scientists aboard his vessels. He was one of the first to publish scientific findings on the Gulf Stream. Using Bache's information as a starting point, researchers over the next decades began to ask questions about the dimensions of the stream. Early current meters showed not only the direction of flow, but for the first time measured variations in velocity. More help in understanding the stream came from an unlikely source. In the late 19th century, sailing vessels by the hundreds were disabled by disasters such as storms or fires on board and were abandoned adrift in the sea. Many derelicts, especially those loaded with buoyant lumber, drifted thousands of miles carried by the currents. These derelicts were hazards to navigation, so ships sighting them carefully reported their positions. Collections of these early records have been examined recently at the Woods Hole Oceanographic Institution by Dr. Philip Richardson.
We have two derelict trajectories here. The first one started in 1885 and went right across the Atlantic, all the way across, about 10 months to do that. The second one lasted even longer. This one is about 3 years. Started here in the Gulf Stream, went eastward, then south, and returns westward, south of Bermuda, and then gradually gets caught up in the Gulf Stream and heads off again when it was spotted for the last time. And that one lasted 3 years, so it was a total trajectory of 3 years. And we have over 200 of these. And when we add them up, very interesting, you can see. So this is the summary of all the 200 trajectories over a 20-year period. And when you superimpose them like this, you can see some definite patterns. Here's one. Sort of see the Gulf Stream moving east. When it reaches south of Newfoundland, it breaks into two branches. One north of the Azores, sweeping over to Europe. Second one moves south of the Gulf Stream, moves south and then around the gyre. Typical time for that circuit is about 3 years. Typical time for the drifters, the derelicts that went from Cape Hatteras over to Europe, was about 10 months.
Derelict tracks help clarify the patterns of surface currents in the Gulf Stream gyre. But to go beneath the surface, in water that can be more than 2 miles deep, requires other forms of measurement. The Woods Hole Oceanographic Institution on Cape Cod is renowned as a leading center of marine research, and one which has a 60-year record in Gulf Stream studies. The institution's first ocean-going vessel was the steel-hulled ketch Atlantis, for several years the only American ship specifically designed for blue water research. Measuring the sea is enormously difficult. For one thing, the surface is rarely calm. The Atlantis had few amenities. Her decks were crowded with winches, wires, and whatnots needed for research. Some of the devices were the latest developments in the scientific technology of the 1930s and 40s. Others were in operation before the turn of the century, and in sophisticated form are used today. These water-catching bottles, equipped with thermometers, gave researchers information about water salinity and temperature at various depths. By comparing data on these properties from several locations, oceanographers could estimate the movement of currents beneath the surface. They were beginning to make headway in understanding what they could not see, the deep ocean. Today's state-of-the-art temperature scanners are apt to be circling the Earth 1,000 kilometers or more out in space. They measure the differences in infrared radiation from the ocean's surface, and their data can be worked into images of entire current systems. Franklin wasn't far off. This infrared image shows the Gulf Stream system. The warmest water, which is represented as bright red, is found in the Florida Current. Most people think of the Florida Current as the Gulf Stream, but oceanographers place the stream's beginnings further north, near Cape Hatteras off the coast of North Carolina, and its end off the Grand Banks of Newfoundland. The Gulf Stream has been viewed as a river in the ocean. While this is not an accurate description, it's easy to see why the idea persists. We call the current the stream. We call its writhings meanders. We often refer to the rings that form when the meanders pinch off as eddies, warm core eddies inshore of the current and cold core eddies offshore. But because the Gulf Stream is part of an ocean system, it responds to a different combination of driving forces than do actual rivers. Radiant energy from the sun is the prime influence on both the Earth's ocean and its atmosphere. That energy heats the Earth unevenly, warming the tropics more than the poles. Warm air rises, cools in the atmosphere, and descends. This movement creates a phenomenon known as atmospheric cells. The spin of the Earth, acting on these cells, helps create prevailing winds that are the principal driving agents of surface currents in the ocean. The winds in the North Atlantic that shape the Gulf Stream are the northeast trades that Columbus and Welcome sailed, and the westerlies that carried Spanish galleons home. These wind-driven surface currents are forced into an elliptical shape, a gyre, by the continents that border the Atlantic. The gyre is also influenced by the rotating Earth, which combines with the wind action to produce intensified currents on the gyre's western arc and creates the Gulf Stream, about 50 to 100 miles wide and a mile or so deep, extending from Cape Hatteras to Newfoundland. This narrow yet deep current separates the warm waters of the Sargasso Sea from the cool waters off the North American coast. Similar forces lead to the atmospheric movement patterns familiar to us from weather reports. In fact, scientists view the atmosphere as a fluid, like the ocean waters, subject to the same physical laws. Yet the action of the Gulf Stream, in contrast to the atmosphere, is much more difficult to study. For while seawater is home to many organisms, it is hostile and dangerous to man. The ocean is about 900 times denser than air, and pressure at the sea bottom can be more than 1,000 times greater than at the sea surface. Salt water can corrode oceanographic instruments. For these reasons, progress in oceanography has come hard. Yet it has come. Marine science now stands where meteorology stood a few decades ago, at a breakthrough point in understanding its uncooperative fluid. Modern oceanography does much of its work with sophisticated ships carrying specialized equipment. This research vessel, like her predecessor, the Atlantis, is essentially a platform for science. This is the RV Endeavour, operated by the University of Rhode Island. The Endeavour's mission is to transport a group of scientists to the Gulf Stream near Cape Hatteras, where they will remain for several weeks conducting their research. Their long-term goal is to understand the dynamics of the stream so that they can predict its behavior. This large orange object, a buoy, was placed in the Atlantic waters about 2 months ago. Suspended below it is an array of instruments at varying depths. In operation, the buoy itself usually floats not on the surface, but is anchored about 500 meters below. The first task this night is to get the buoy and the instruments attached to its cable safely on board. Out of the water, it weighs about a ton. This technician is sending an acoustic signal that will release another device from its anchor close by, where it has been gathering data on current flows in the Gulf Stream. Once on the surface, this instrument, called an inverted echo sounder, or IES, is hard to spot. Technicians use a radio tracking device to help them find it.
Right there, yeah, straight ahead.
It's essential for the ship to retrieve the IES quickly. Otherwise, the current will carry it out of range. Since most radio waves don't carry underwater, the IES uses sound waves. Differences in temperature change the speed at which sounds move beneath the surface. The data stored in the IES housing give the scientists information about the constantly shifting location of the current. Other oceanographic instruments aren't anchored, but drift freely with the currents and trace their paths. Scientists at the University of Rhode Island have developed one such instrument, which is called a Raphos float. This one is about to be pressure tested prior to deployment. Its housing is made of Pyrex glass, which can withstand the enormous pressures of the depths. In seawater, temperature is closely related to density. Cold water is usually denser or heavier than warm water, and water under the surface flows in layers largely determined by density. As the model shows, the Raphos can be set to move along a density layer. The blue water is cool, the red warm. In actual operation, these modern devices have demonstrated that the flow of the Gulf Stream is smooth near the surface and turbulent at depth. Like the inverted echo sounder and the Raphos float, this instrument, still under development, is a proxy for man in the hostile medium of the sea. Called a tomographic transceiver, this unit is part of a system that transmits and receives bursts of sound and measures the tiny variations in their speed influenced by movements of water under the surface. The device will be deployed at various depths and will collect data for months before being recovered. Scientists hope that arrays of the tomographic transceivers will give them three-dimensional images of circulation under thousands of square miles of ocean. This transceiver is ready to be shipped out for sea trials. Together with other sophisticated instruments, some of which you've seen, it forms one part of an oceanographic triad. The second part, of course, is the ship. The third, the satellite. Satellites have given oceanography a breadth of vision that would have astonished the early investigators. Ships and buoys can cover only a small patch of ocean at one time, but orbiting sensors can observe entire ocean basins, and that is essential to the future of marine science. Some satellite sensors can measure differences in sea surface height caused by changes in gravity or, at finer scales, by wind action. Elevations and depressions in the sea surface can influence circulation patterns. Other scanners measure the temperature of the sea surface. The University of Miami is a major receiving center of the satellite data. Dr. Otis Brown and his colleagues use sophisticated computer programming to turn the data into maps of the world ocean.
And we're going to start by looking at some ocean color results. What we're going to look at now is a monthly average sea surface temperature field. The way it's coded is the warmest temperatures are in the red, the coolest are in the blues. This corresponds to a range of about 2 to 30 Celsius. I would note as the globe turns around that you'll see that in this monthly composite that the ocean is anything but uniform in temperature. Now we're going through a time series over 15 months. Then we're going to zoom in on the northwest Atlantic where there are warm rings that propagate.
The Miami program is also used to show the stream's meanders and their offspring, the powerful rings or eddies, which are to the ocean what storms are to the atmosphere.
And this is the ring signature in the thermal field, and you see it turning in a clockwise direction, eventually coming down towards Cape Hatteras where it's assimilated.
While Brown's group in Florida is focusing more on the big picture, other investigators use the satellite data to address more detailed questions. Here at the Graduate School of Oceanography in Rhode Island, a team headed by Dr. Peter Cornelian has used readings of sea surface temperatures to develop a computerized animation of Gulf Stream movements. The warm Gulf Stream is reddish. The slightly cooler Sargasso Sea is brownish, and the coolest coastal waters are in the blue range. Like other oceanographers, Cornelian augments his satellite data with measurements taken deeper underwater. Measurements made by the inverted echo sounder. That information, represented here by temperature contour lines, closely parallels what the satellite reveals of Gulf Stream movement. Further validation is provided by Rafos floats. The symbols moving in this image represent the floats as they drift at varying levels in the stream. Such imagery gives researchers an accurate idea of relative current speeds in the main flow and in meanders and rings. Computers enable oceanographers to see entire features of oceanic circulation that until recently they could only measure bit by bit. New techniques like these are helping scientists gather the data they need to develop valid theories to account for the complexities of the Gulf Stream. Oceanography is beginning to move from description to theories that can explain fluid movements on increasingly larger scales. One of the science's most respected theoreticians is Henry Stommel of the Woods Hole Oceanographic Institution. Recently, Stommel has been working on a concept to explain one of the most perplexing of oceanic functions, how warm surface water becomes cold bottom water.
So we want to think of the ocean as a succession of layers. We could start by tracing a particle of water that begins in a warm layer at the top near the surface, say right here in the North Atlantic. It sinks down and goes along like this under warmer layers at the surface now, and then up in the Gulf Stream where it goes quite fast and comes out here and cools. And so as it goes around, it subducts into an even deeper layer, cuts under the trajectory of the other one, then back up in the Gulf Stream and comes out further north. Here it cools again, sinks down, cuts under at an angle there, under the other trajectory, and then goes up further north. Some of it can even go across into the Norwegian Sea. There it sinks to the bottom and comes back as a narrow current hugging the continental slope in the deep portion of the ocean.
The deep undercurrent Stommel describes is part of what oceanographers think of as a furnace-like system that carries warm water poleward on the surface and brings a return flow of cold water back along the bottom toward the equator. Yet despite the work of theoreticians like Stommel, the ocean is still largely unobserved and unexplained. To help fill in the gaps, scientists today make use of high-speed computers that can simulate entire current systems. This is a model of the Gulf Stream developed at the National Center for Atmospheric Research. The model combines known laws of physics with observed data to simulate the movements of meanders and eddies. Oceanographers believe that such modeling can explain how these structures are formed. Computer models also have practical applications. Combined with the hard data from physical oceanography, they provide a valuable asset for naval strategists the world over. Submarines have become one of the most powerful of modern warships. To detect them, navies have traditionally relied on the sounds they produce as they move through the water. But changes in temperature and density, such as those found in subsurface layers and boundaries of the Gulf Stream, alter the performance of sound waves propagating through the sea. These layers and boundaries, called fronts, make fine hiding places of Gulf Stream meanders and rings. If you know where they are, you know where to hide your subs and where to find theirs. Satellites are helpful in locating fronts. But satellite sensors only read the skin of the sea. To find out what is happening below, scientists and military planners use an airdrop probe called the AXBT. The probe includes a buoy with radio and antenna. The instrument yields a profile of temperature with depth that indicates the boundaries between water masses. AXBT information from the Gulf Stream is forwarded to Harvard University. Modelers at Harvard combine the weekly survey of temperature readings from the AXBTs with infrared satellite images and an advanced computer model to create a system for predicting the never-ending changes in the paths of meanders, eddies, and the main current of the stream. The lab is headed by Professor Alan Robinson, who has spent more than a decade developing techniques of modeling the Gulf Stream. Robinson calls the work Gulf casting.
I know it's early, but there's a reason why I want to see what.
In Gulf casting, the Harvard team lets their model run into the future. Reconciling its forecasts with real-time observations, the model stays accurate for weeks, and performances are improving.
That's the power of the model, kept on track by continually adding critical data information from satellites and from below the surface by airdrop probes. We're actually using the model to make dynamical forecasts, much as meteorologists do numerical weather prediction in the atmosphere. In fact, the internal weather in the Gulf Stream region are the rings and the meanders themselves. Those are the weather systems.
The image on the top of the screen is the Harvard Gulfcast for a 7-day period. The image on the bottom represents actual conditions in the stream as indicated by observations at the end of those same 7 days.
Data assimilation is clearly the future of oceanography. And here in the Gulf Stream ring and meander system, we actually have it operating for the first time in oceanographic history.
The Harvard Gulf Stream forecast is relayed to the Navy, which feeds the material into its anti-submarine warfare program. In addition to its military use, the information produced by oceanography's new analytical techniques has a large and growing commercial application. So important is this information that the National Oceanic and Atmospheric Administration, or NOAA, produces a daily chart describing what is going on in the Gulf Stream region. Offshore oil rigs prospecting in increasingly deep water need to know when strong eddies threaten their vulnerable drill strings. Tanker captains use it so they can save time and fuel by hitchhiking on the stream's strong currents. And fishermen rely on the data to help them spot eddies and other structures where their catches congregate. As part of the study of the Gulf Stream, marine scientists are investigating the influence it exerts on flora and fauna. They want to know if the Gulf Stream is a habitat for life or just a highway where organisms drift. The Gulf Stream does carry many species far north of their normal ranges. This tropical butterfly fish, usually found in the Caribbean, is swimming in waters just off Cape Cod, Massachusetts. Some species hitchhike on the current. Giant bluefin tuna ride it from their wintering grounds in tropic waters to their summer feeding grounds off New England and the Canadian Maritimes. It appears that some individuals use the currents to cross the entire North Atlantic. Turtles, too, are often found hitchhiking on the stream. Some may actually travel around the full ellipse, returning to their home beaches in the Caribbean region. Yet many migratory patterns of creatures in the ocean are still shrouded in mystery. None more so than the eel. Eel larvae drift with the North Atlantic subtropical gyre before entering coastal rivers. The American populations take about a year to make their journey to fresh water. The European eels take about 3 years. When they reach maturity, they must go back to the sea to spawn. Scientists have surmised that American and European eels return to the Sargasso Sea to spawn because their larvae are found there. Yet no adult eel has ever been seen in the area. One hypothesis is that the eels swim at great depth, taking advantage of the deep water currents. On a research mission, the submersible Alvin descended 2,000 meters to the sea floor. These rare pictures of adult eels were taken near the Sargasso, and they were in very deep water. Yet these few photographs do little to resolve the mystery of the eels. Biologists are also looking at another phenomenon, the edge effect. Nutrients, plants, and animals collect along the boundaries formed by differences in properties like temperature or even by wind. Fish of all sizes gather along these edges. Currents, like the Florida current below, also catch up and transport plankton, the small plants and animals at the base of the oceanic food chain. Historically, biologists have collected specimens and kept them in laboratory tanks for observation. Much of the collection work has been done with a net. Yet nets tend to catch what one marine scientist has called the weak, the blind, and the unlucky. The lucky and the agile tend to escape. And nets can be rough on what they do catch. For these reasons, some biologists dive for their specimens. Dr. Lawrence Maiden and his crew from Woods Hole are frequent visitors to waters bordering the eastern side of the Florida current. Maiden and his associates are experts in what is called tether diving. This technique was developed for work in the open ocean, where free divers would soon disperse beyond the dictates of safety. There is no anchor on the line, just a weight 100 feet down. The ocean here is more than a mile deep. The tethers enable each diver to drift with the rest, yet provide a good deal of room for individual collection or experimentation. Maiden concentrates his research on organisms the net would crush into jelly. Creatures like the Venus girdle, Medusa, Ctenophore, and Maiden's specialty, the salp. The salp is a common wanderer in warm and temperate seas. Like other plankton, salps are often caught up in the stream and drift with it far from their natural habitats. Many eventually perish as the stream cools beyond their tolerance, or when an eddy breaks off from the current and carries them into alien water. Some of the questions Maiden wants to answer have to do with such involuntary migration, others with the salp's reproductive and feeding habits. A safety diver keeps station near the ring to which the tethers are attached. She is the lookout, keeping one eye on the divers and the other on dangers beyond. Sharks sometimes show up. They have never harmed Maiden's divers, who regard them as part of the biota, but a potentially dangerous part. This one has his curiosity up, so the safety diver calls for defensive action. The divers form a protective ring. The shark is less likely to attack a group. Sometimes, sharks will follow a piece of bright metal down and away from the tethers, but not this time. With this kind of attention from a predator, it doesn't make sense to continue the dive. Is he a salp?
Yeah, these are salps
These
too.
are chain of salps. Now, do
Chain
they
of-
change from individuals to chains to individuals again?
Well, they're sort of born by a budding process, so they're born as a chain.
The salp is a sea animal, part of a vast group of organisms known as zooplankton. It and other similar creatures in the oceans feeds mostly on plants. Billions of tiny sea plants called phytoplankton that use sunlight to produce chlorophyll. Satellite scanners sensitive to green pigment can measure variations in chlorophyll, enabling scientists to show how concentrations of plankton change according to region and season. One of those scientists is Otis Brown of Miami.
We're going to look at some monthly sea surface pigment fields or chlorophyll A fields that have to do with biological productivity in the ocean. The new thing that we now have with this view of the ocean is the fact that we can look at the biological response on a number of different time and space scales, which just weren't accessible with ship observations. For example, if you look at the Gulf Stream front here, you see that although we have known it principally as a physical phenomena in terms of the meandering, that in fact the biological fields are responding in time and space too, the same way that the temperature field responds. I mean, we've known from the biogeographers that this was a boundary, but we've never had this kind of picture that showed that, no, it's not a smooth, straight line, that in fact every time the Gulf Stream meanders, that this boundary is meandering between the more northern species and the subtropical species.
This image shows that the biological boundaries of the Gulf Stream are constantly in motion, and that they depend on the physical processes of the current as it flows from the tropics toward polar regions. The Gulf Stream meets the north here, off the Grand Banks of Newfoundland. The current, still freighted with warm water from the south, sweeps near the banks. The Labrador current comes down from the north. The temperature difference is dramatic, as much as 40 degrees. So cold is the Labrador that it carries a threat to shipping, a hazard this Coast Guard plane is assigned to monitor. The plane is part of the International Ice Patrol, and the mission of its crew is to search for icebergs.
15 seconds, solar overhead.
Each sighting is reported, and vessels in the busy sea lanes nearby are warned of birds drifting close to them.
Here's undoubtedly one that broke off from the larger berg.
Some bergs float down on the Labrador current to the stream, which melts them. In these subpolar conditions, the Gulf Stream's release of enormous amounts of heat to the atmosphere creates fog and sea smoke. The Gulf Stream's heat mechanisms also affect weather along the eastern coast of North America. Warm air rising from the stream and nearby waters sometimes interacts with cold air masses to produce winter hurricanes, like the famous blizzard of 1978, which dumped as much as 4 feet of snow, immobilizing the entire northeast coast. But mostly the stream affects long-term weather patterns, climate, and the effects are most noticeable in the lands downwind of the current system, Europe. Some of the warm water brought north by the stream enters current flows moving toward Europe. It's long been assumed that this is what makes the European winters so much milder than their latitudes would indicate. But scientists believe the phenomenon is more complex than that and involves the Earth's other major fluid, the atmosphere. Even without the Gulf Stream, cold winds coming off Canada would be gentled by the ocean. They would create a maritime climate in Europe with relatively mild winters. But with the stream's contribution of warm water from the south, Europe benefits even more. This interaction between atmosphere and ocean has even more profound implications, including global climate change. The last great ice age peaked 20,000 years ago. Core samples taken from the seafloor provide a record of shifts in the habitats of certain tiny organisms during cycles of glaciation. Using these records, researchers speculate that during the last ice age, the Gulf Stream system fluctuated wildly. At times, it was restricted to a more southerly route from Cape Hatteras straight across to Spain. Climate has continued to change in the intervening centuries. North America and Europe underwent a little ice age lasting from roughly 1450 to 1850, when winters were far more severe than they are today. Those were natural variations, but today scientists have come to the conclusion that some climatic changes are the result of human influence. In the past, gases like carbon dioxide, naturally produced, helped to keep the Earth warm enough to sustain life. But today, man and his machines are producing increasing quantities of CO2. And now, scientists fear that the amounts of these gases in the atmosphere will produce a global warming or greenhouse effect. The ocean absorbs some of the excess carbon dioxide from the atmosphere. Marine organisms take up part of it, and some is carried by cold seawater to long-term storage in the abyss. So the ocean could, at least for a time, slow the planetary warming. But what might happen to the Gulf Stream system and to world climate if the ocean's storage capacity for greenhouse gases is exceeded and global warming becomes severe? While no one really knows, there are two opposing scenarios of what might happen. Scientists are fairly sure that warming will be greater nearer the poles than near the equator. This would shrink the temperature differences between the two areas, and that could weaken the prevailing winds. Weaker winds might mean a weaker Gulf Stream, and the amount of warm water brought north by its current would shrink, and Europe would get colder. In another scenario, atmospheric warming near the poles might cause the warm surface water of the Sargasso Sea to expand northward. Winds blowing over the pool would warm Europe. We must reconcile scenarios like these if we are to become skillful stewards of the planet. But we still don't know enough to understand the essentials of planetary maintenance, the interaction between ocean and atmosphere. In the past few years, oceanographers and meteorologists have begun to address the problem. They are embarking on what they call the World Ocean Circulation Experiment, a multi-year effort designed to answer many questions about air-sea interaction. One of the project leaders is oceanographer Carl Wunsch of the Massachusetts Institute of Technology.
For the first time in history, it is actually technically feasible to think about viewing the ocean as a single connected fluid that is interacting everywhere with the other global fluid we have to deal with, the atmosphere. The World Ocean Circulation Experiment is going to take advantage both of old and new technologies. That, for the first time, will give us the equivalent of a global barometric network. Within a few years, we believe, of modeling entire ocean basins, ultimately the world ocean, much as meteorologists are now able to model the global atmosphere.
Once completed, this international program will go a long way toward making the ocean as well observed as is the atmosphere. Those observations and the theories they generate may at last give science an analytical and predictive tool that would have been unheard of only a few years ago. For now, we end our story where we began it, on the west coast of Ireland, where sea and air allow the cultivation of plants that have no business growing here, where sea and air conspire to bring seeds from the Caribbean thousands of miles around a great gyre to a beach near Galway. We know far more of air and sea and of the Gulf Stream than we did 500 years, even 5 years ago. Our curiosity, as always, spurs us to learn more. We're constantly struggling for discovery, like Christopher Columbus. The question before him was a formidable one. how to conduct, how to survive a passage into the unknown. The question before us is also formidable: how to preserve a planet. Like Columbus, some of our answers will be wrong, and some of them will be right. And, like him, we'll be voyaging.
Funding for NOVA is provided by the Johnson & Johnson family of companies, supplying healthcare products worldwide, and Prime Computer, supplying integrated computer solutions to the world's manufacturing, commercial, technical, and scientific marketplaces. Major funding for NOVA is provided by this station and other public television stations nationwide. For a transcript of this program, send $5 to NOVA Transcripts, Box 322, Boston, Massachusetts 02134. Please be sure to include the show title.